that the unitary group, by having those discrete subgroups, then has the characters that correspond to polygons that have the symmetry whatever. If it's UN, then inside there's a polygon with n sides, sort of waiting to. But the truth is, when you have a UN symmetry, its weight and root space are many dimensions. U2, it's basically one dimension. U3 is two dimension, makes hexagonal figures. Okay, that's the quark symmetry for high energy physics, but it's, for me, it's the symmetry of the p shell of an atom, which has a triplet that has unitary transformations. That's the most obvious use of U3. The stuff with the high energy is not obvious.
I didn't want to, I was more looking at this as sort of a window into the continuous group by looking at or using indices of the finite groups. Mm-hmm. We can do we indeed span the entire U2 if we use every one of those infinites of groups?
Well, all the groups that I showed here are groups that are made out of symmetry that lives in our good old real three-dimensional space. So that means that I'm working with the group R3, rotation 3, but rotation 3, as you know, is covered. That is, it has a +1 and then a -1 phase associated with U2. So U2, that spinor space, has a funny, what's called homomorphic relationship with the three-dimensional real space that has the spin vector and the Stokes vector and the stuff that we would just call ordinary angular momentum. So if that's all you ever learned was that you had a three real dimensions, you would miss all of the stuff that having to do with the half-integer angular momentum that U2 has. Mm-hmm. But U2 also deals with the integral momentum as well. They are just as good for them as they are for the R3. But the R3 doesn't recognize the halves. Okay? Now, then it comes to look at the multiplication structure of the either one of these groups, and the one that is pretty obvious is that the U2 just has spin up and spin down. Now it really should be plotted that way, so it's a two-dimensional complex space. That's our phase space for two-dimensional harmonic oscillator, right? But looking at it like this, I raise angular momentum -0.5 by 1 unit, and I get +0.5. So that's the what we might call the fundamental weight diagram of the Lie algebra associated with U2. Now you take another dimension of those things. Now you start making triangles and hexagons and things like that to describe all of the quantum numbers of U3. Now, most people in high energy physics, they would say, oh, well, that's Gelman's eightfold way U3 symmetry for the hadrons. And it turns out the mesons and so forth, that was a big deal to discover that. That was discovered both by Gelman and George Zweig, sort of simultaneously. You never hear of George, but you hear lots about Gelman and Neyman. They were within 50 feet of each other at Caltech. You know, strange history. Okay, but then that keeps getting bigger. The next stop is U4. U4 is a tetrahedron. U3 is a triangle of the quarks. U2 is spin up and spin down. U4 is used to describe the standard model. Okay, it starts with a tetrahedron. We use it to describe spin 3 halves. That is multiplets of spin 3 halves for the hyperfine structure and stuff like that. Which you helped work on some of that stuff. And so on. Then the polytopes that describe them become 4-dimensional, 5-dimensional, 6-dimensional. You see, this is all Lie group theory. Okay. This U2 is the simplest Lie group. R3 shortly thereafter is the next, I would say, next simplest. And then it's a question of what subgroup, what finite subgroups that live within. Just as in any real line are all these fractions, right? See, so the real line to the rationals becomes very important. It's almost too much. It's a wonder we don't give up sometimes with these things, because there's so much. It's a galaxy of thought.
I see it as being rather addictive, because you see the potential and you
Yeah.
want more.
That's right. Yeah. No room for boredom.
How does the relationship between the rational and the real line, or what is the relationship between
Just
that comparison and then the root?
my quick answer would be the same one that we saw when we looked at the CN and those waves making the quantum fractals. That was just one dimension, right? Well, one dimension of space and let time run. So, in a sense, it was two-dimensional, but that's where you're letting the waves discover the rationals that exist in 0 to 1, which would be the circumference of the Bohr ring upon which the wave moves in the open system. Does that make sense?
I think so. The fairy sums and those rationals are,
Yeah.
they converge to real
And
lines.
as long as you
They're
excite,
dense
yeah.
in the real lines.
Yeah.
You can run a sequence in the rationals and hop to any
Yeah.
you can approach it as a sequence.
So that's the simplest case of one spatial dimension, right? And then the time exhibits the how the fractions relate to each other, because the slopes have to be fractions. Now you go to 2 dimensions, you're going to have this stuff in a volume, right? And then so on as you go to higher and higher symmetry. They're always going to be there. The rationals are always going to be there, lurking.
It's like the waves are making up.
And the waves in there are going to respect them. They have to, because they have to fit. They have to be eigenfunctions. It's a matter of fitting. Yeah. That's where the symmetry really works. They don't resonate if they don't fit, right? Yeah. So, yeah, it makes simple. Sort of sounds simple in when you describe it in bit by bit, but it starts to pile up.
It's very strange.
Yeah, it is. It really is. Okay.